this is the second section of the third chapter named the mean value theorem. Now before we can see the statement of the mean value theorem and prove it, we need to see a special case of the mean value theorem, which itself has its own name. In fact, this is what was found first. It's called Rolle's theorem. So let's see what its statement is. Here we have a function f y equal to fx, that means just a function f, which is given to be continuous in a closed interval a comma b. And you do understand in this context that a is less than b. Those things are already understood. So f is continuous throughout this closed interval at every point, and f is also differentiable in its interior in the open interval. Now with all these, if f vanishes at these two endpoints, that is f of a and f of b are both 0, if that happens, then there exists a point c in this open interval at which the derivative of the function will be 0. And it also makes sense because it's already given that f is differentiable at every point of this open interval. So derivative exists, but there will be at least one point in the open interval where this will be 0. That means if you think of the tangent to the graph of the function, the tangent will be horizontal at some point in the interior of this closed interval. Now let's prove this. Because it's given that f is continuous in this closed interval, we can appeal to the max-mean theorem that we already know from the previous section. It guarantees that the function then attains an absolute maximum value and an absolute minimum value at some points in this closed interval. Now our knowledge from the previous section, we also know that these extreme values are attained at three types of points. An interior point x where the derivative exists and is 0, an interior point of x where the derivative does not exist, and at the endpoints a and b. Type 1 and type 2 are the critical points. Now it's given that f is differentiable in the open interval, that means in the interior. So there is no question of having points of type 2, because type 2 is those points where the derivative does not exist and which are also interior points. Such points do not exist for this type of function. So that leaves us with only points of type 1 and type 3. If we have points of type 1 where some extreme value is attained, that means if the absolute maximum or absolute minimum value is attained at a point of type 1, that means it's an interior point, then by theorem 2 of the previous section, the derivative at that point has to be equal to 0. It is that theorem which is our that first derivative test. Okay, but what does it say? You recall that if a function attains a local extreme value at an interior point of its domain where its derivative also exists, then the derivative has to be equal to 0. It's that thing. Otherwise, both the absolute extrema are attained in this set, that means at these points somewhere. What do we mean by otherwise? Otherwise means if the previous case is not the case. Otherwise, what is the previous case? That if either the absolute maximum is attained at an interior point or the absolute minimum is attained at some interior point, then we have this situation. If that does not happen, then both the absolute maximum as well as the absolute minimum are attained at these points somewhere. However, you go back and see the statement, we have this hypothesis also that f vanishes at the endpoints. That means the absolute maximum value has to be 0 and the absolute minimum value also has to be 0. But then all the points, all the values of the function obviously lie between absolute maximum and absolute minimum, so they also are forced to all be 0. So in this case, f is constant, actually constantly 0. We did not write that, or the authors did not write that, because The fact that f is constant is what we need here, because that just means that if we now differentiate f at any interior point x, then we are going to get 0 because f is constant. So you see that in this first case also you get an interior point c where the derivative becomes 0, and in this second case all the interior points are points where the derivative is 0. So you are getting such a c in any case. So that's the proof of your Rolle's theorem. So this is the typical situation. Here the graph of the function f is this. Actually I should not have extended this. Okay, between the 2 points a and b only we are talking about the graph. The function may not even be defined outside the closed interval a comma b. The fact that the function is continuous means that the graph has to be in one piece. It should not be broken. And the fact that it also needs to be differentiable in the interior means that there should not be any sharp points in the graph. It should be smooth like this. Alright, and you see that here this c is an interior point where the derivative is 0 because the slope of the tangent is 0, so the tangent is horizontal. In this case there is only one such point, but that's not necessary. Rolle's theorem only guarantees that there is at least one such point. There may be more than one also, like this one. Say this is the graph of some other function also satisfying those hypotheses. Oh, I forgot to mention one more thing, that the function needs to have 0 value at a and b. That is why the graph meets the x-axis at a and b. Okay. Here also we have the same thing. The graph meets the x-axis at a and b. In between also it can come down and go up and cross the x-axis. The point here is that at a and b the function has 0 value. And also of course the continuity and differentiability hypotheses are there. In this case there are 3 such points. At C1 there is a local maximum, at C2 there is a local minimum, at C3 there is a local maximum, but at all these points tangents are horizontal, or in other words that the derivative has 0 value. And let's also next see what can go wrong if some hypothesis fails. Say this is the graph of some function which is still 0 at both a and b. This point is on the graph, okay, this is a single point. And still in the interior of this interval the function is differentiable because we do not see any sharp corner or bend. At an interior point, okay, we are not even talking about differentiability at end points, where anyway we can only talk about one-sided derivatives. Nothing like that. Only at interior points we are talking about differentiability, and that's there with this function also. But when it comes to continuity, the function fails to be continuous at a. Just that one failure has caused the function to not have any horizontal tangent. You can see that for yourself. Nowhere on the graph do you have any horizontal tangent. So the hypothesis of Rolle's theorem are not fully satisfied here, and the conclusion is also false. Instead, we can have a discontinuity at an interior point x0 also. So of course at that point it's also not differentiable. I mean, I'm talking about the function, whatever function is there behind this graph. And you can see that in this case also there is no horizontal tangent at any point. I mean, at those points, leaving this point, we have other points where the function is differentiable. That means tangent exists, but no such tangent is horizontal. So again, the hypothesis of Rolle's theorem are not fully satisfied here, and the conclusion is also false. So the point here is that if the hypotheses are not all of them are there, then there is no guarantee for the conclusion. The conclusion may still be true. I mean, you may still have a horizontal tangent if you tweak this graph, but you can't say anything for sure. Rolle's theorem won't tell you anything in that case. And things can also go wrong in this other way as well. This time it's continuous everywhere in the closed interval, but it fails to be differentiable at this interior point. Okay, so still all the hypotheses of Rolle's theorem are not there with us in this case, and the conclusion is also not there. There is no horizontal tangent at any point other than this one, of course, because at this point there is no tangent anyway. Let's see an example next. Example 1, where we consider the following polynomial function x cube divided by 3 minus 3x in this closed interval minus 3 comma 3. Since we know that any polynomial function is differentiable at any real number, so obviously this polynomial function will also be differentiable, in particular in the interior of this interval at any interior point. And differentiability implies continuity. So its differentiability at any real number also implies that it's continuous throughout this entire interval. Not just open interval, but the entire closed interval. And additionally, if you calculate f of minus 3 and f of 3, it's a simple thing, you can see that you are getting 0. So here all the hypotheses of Rolle's theorem are satisfied. They are there. So that means it follows from Rolle's theorem that the derivative would be 0 for some c in this open interval. Now because the polynomial is already given, I want you to actually calculate the derivative. Set it equal to 0 and find the points c where this will happen. You please do this. And then what you do next, you go on Desmos graphing facility online. There you graph this polynomial in this interval and see whether you are really getting horizontal tangents at those points that you find by solving this equation for this polynomial. So that's our Rolle's theorem, and next week we are going to use this theorem to prove the mean value theorem, the actual theorem which is more general than this one.